Welcome, Mechanics of Materials students. This is our fourth lecture in yield criteria. So in this we're going to do an example where we look at criteria for yield and basically how much additional load we would have to apply to something that's already in a biaxial stress state if we needed it to yield. So at this point, we've gone over the Tresca criteria for max shear. We've gone over the Von Mises criteria, which uses deviatoric strain energy to define a combination of normal loads in multiple directions. In our case, just two, because we're doing plane strain that would lead to yield. We've compared Tresca and Von Mises in terms of which is more conservative, overlaid them in a plane stress state, for applied loads being equal to principal stresses, so no applied shear. Now we're going to apply this to a case where we have numerical considerations. So we've got an aluminum block. It's a plate, so it's much wider and taller than it is thick. We have fairly thin edges in this case, and it's 20 millimeters thick, and we have some distributed loads along the edges. And we have some dimensions for it. So we are asked, and we are told that in addition to these loads, we have a temperature increase of 100 K. We have no restraint in the Z direction, so we're in plane stress. So we're asked to find how much additional load in the X or Y, that's X or Y, directions are needed to have yield. So we're asked, hey, yield criteria would be nice because we have a biaxial stress state and we need to relate that to a uniaxial stress state that was used to define the yield stress that we might have looked up in our handbook. We have no applied shear, so we know that our applied stresses of negative 10 megapascals, that's 200 kilonewtons per meter, times our or divided by our width or our thickness of 20 millimeters, and we have our 50 megapascals coming in tension in our Y. So how much additional load would we need to yield? We have no applied shear, so our applied normal stresses are our principals. So if we're thinking of a Mohr circle, we're on that x-axis. Okay, so here's our critical takeaway. We looked up in a handbook and we found the value of sigma yield, sigma y, is 300 megapascals. What that means is somebody took a bar and they applied a uniaxial tensile stress to that and said, yea, verily, when I yank this in tension and I apply 300 megapascals, I get yield. I measured it. I did a stress strain curve, and that's where I deviate from proportionality of stress and strain. What this value corresponds to is our Y value on our Tresca criteria. The actual max shear for this test condition, if we drew our little test specimen on a Mohr circle and we put tau up here and we put sigma down here, and this is the test specimen that was used to get this sigma yield of 300, we would have our sigma, basically if this is the Y direction, we know for our test case, our uniaxial tension is being done in the Y. Our sigma x and sigma z are both 0, and so our sigma y is right here. It's a principal stress. And we know that the max shear that corresponds to that 300 megapascals is 1/2 of the 300 megapascals, because the 300 megapascals is down here, it's a principal direction, and we know that the max shear that corresponds to that, which is going to be experienced on a plane that just happens to be 45 degrees up here, so 90 degrees on the Mohr circle, 45 degrees on the part, that's by definition 1/2 of sigma y. Okay, so the max shear that goes with that 300, because we know how it was tested, is 150. So now we have a max shear that we can say, okay, well, If that's the max shear that causes aluminum to yield, what's the max shear on our biaxial load state? We can use a Mohr circle to determine that and step through. So that will be the basis of our Tresca yield criteria. So our Y Tresca is 300 megapascals, which corresponds to twice the max shear. And we know that our max shear for our biaxial loading is going to be 1/2 of the difference between our applied X and Y loads because they're in different directions. So we're kind of on one of those sloped parts of the Tresca hexagon. So all we have to do is subtract X from Y, take 1/2, and we'll get our tau max, and we can compare it to what tau we would need to yield. So 150 megapascals is the shear needed, the max shear in any direction needed to yield. That will have to be equal to 1/2 of the difference between our applied normal stresses. So we got, it won't yield. We're quite a good ways away from that at this point. If we were to take what we've got a sigma XX of -10, a sigma YY of 50, so we're applying 30 megapascals. So we got 50, or excuse me, yep, 50 minus -10 is 60 divided by 2 is 30. So we effectively have a factor of safety of 5 at this point against yield in the current state. So what would we do to make it yield? What if we wanted to form it? We need to know how much additional stress we need to apply to form it, say. We wanted it to yield. Well, we could basically keep either one fixed, or we could change both. So if we started just hypothetically and said, okay, we're going to keep our sigma YY fixed at 50 megapascals, then what would we need, how much more compressive stress would we need to go up to our yield point? Well, all we have to do is put in our 50 for our sigma YY, keep what we know our shear that corresponds to yield is, which is 150, and then solve for sigma XX, and we find we have to go up by over an order of magnitude. So from -10 to -250. And we can do the same thing if we keep our sigma XX fixed at -10 megapascals. We can insert that in here in our expression for our Tresca yield criteria, and then solve for sigma YY, and we get, again, something significantly larger. So we can change them both. So we can create a mathematical expression for how much we would have to increase our actual shear and look at those proportionally. So again, we calculated our actual max shear within the part with the applied stresses of -10 megapascals and 50 megapascals respectively. We'd need 150 for yield, so we've got to increase the shear by 5 times. So basically what we could do is increase both the Y and the X by a factor of 5. So any one of those. So basically what we did was we just defined that Tresca hexagon, and this factor of 5 would actually be the slope in the sloped part of the sigma XX versus sigma YY portion of the Tresca irregular hexagon. So let's do the same thing with Von Mises, again relating which parts of our test data correspond to which parts of the yield criteria expression. So we know that from Von Mises, if we're looking at plane stress, we've shown in our derivations that this combination of expressions for applied stress constitutes at least a simplified version of our J2, our deviatoric strain energy. We've only got stresses in 2 directions, and we have no applied shears. So that's all we have contributing to our deviatoric strain energy, and we know that that has to be equal in this case to our y squared. So for yielding, y, because just generally our Von Mises criteria would have to be our J2 would have to be equal to this K squared from our Von Mises. What we're doing is saying, hey, wait a minute, I know something about this material. I know that it yielded when a uniaxial test was done to a value where my uniaxial stress was 300 megapascals. So I'm going back and doing what we did at the end of our Von Mises discussion, saying I'm going to insert a known yield criteria that is based on a uniaxial loading, which I can relate to a Y from the Tresca criteria, which says uniaxial stress, in this case applied uniaxial stress of 300 megapascals yielded. Okay, so that becomes my K2 for Von Mises, and so I can insert that here. So now all I need to do is crank through my values. I know what sigma xx and xy are, so I could show how far below it I was, but the question said how much would I have to change something to yield. So I'm going to go through the same exercise I did with Tresca. We'll start by keeping our sigma yy fixed at 50 megapascals and solve for sigma xx, and so I get a quadratic expression, and I solve for sigma xx, and this time I could either go more compressive, or I could go to the other way and apply a significant amount of tensile stress. So I actually get two values from this. And I can do the same thing with solving for my normal stress in the y. If I kept my normal stress in the x fixed at compressive 10 megapascals, then I would have to up my normal stress in the y from 50 to either negative 295 or positive 305 to achieve yield, to have this expression be equal to 300 megapascals squared. So again, this is the most important part of this whole exercise, relating the applied stresses, which constitute your deviatoric strain energy, your J2, to some criteria that says if I have this value, I will yield. And in that case, we were able to relate a uniaxial test where we were able to use that Y value that we had measured. And we can go through, I'm not going to step through the math here, but you can go through a mathematical exercise using these two parabola expressions and say, what if you change them both at the same time? Is there some ratio of change that you could get, that you could change x and y, sigma xx and sigma yy together, and basically be right at, defining yield. And you can walk through that, and you'll find that what you've basically done is trace the Von Mises ellipse. So that is an example of use of Tresca and Von Mises yield criteria in defining when will you yield, what type of actual real loading. This time it was complex in that it was biaxial. And our yield stress that we got out of a handbook was uniaxial, so they weren't comparable. But we had to relate them through their common point, which is max shear to max shear. What's my max shear in my biaxial loading? How does that relate to my max shear in my uniaxial tension test loading that I got out of my handbook? And the same way with the deviatoric strain energies. So we related test data from a handbook to real data from a real loading scenario through this criteria of either deviatoric strain energy or max shear that brought them together with what makes yield. So that's basically how you use the concept of yield criteria. And obviously Tresca is a little bit more simple and straightforward. If you just need to get an estimate, and it is more conservative, so that has that advantage. So that is it for our discussion of yield criteria. We will pick up one more topic, and that is failure criteria, which is going to basically be a little bit of a nuance off of our Tresca expressions, and we're just going to basically look at ways to use our Mohr circle and use our Tresca yield concept to explain when we think something's going to fail. And so we're going to go beyond yield, and we're not going to be looking so much at max shear, which is what makes things deform, but we're going to look at max tension or compression under cases under which things could fail. And so for that, we'll be linking very hard back to experimental data. So we'll kind of be using the much more the principal directions of our Moore circle, which are the things that make things fail. So stay tuned for that. And that will conclude our yield and failure section of our course discussions.